Hi guys, I'm back. I thought I'd make a video since I've gotten really behind. This has been kind of a busy week. That I would just make a video and just kind of go through and kind of reply and answer some of the comments and stuff. First and foremost, I just want to thank all of you for commenting and for your gracious words and stuff and everything. The very first one really basically was not really a comment in here. It was actually a message that was sent to me, and it had to do with measuring negative voltages and how you go about doing that, such as grid voltages. And I thought I would answer that real quick. Basically, when you do voltages and you're checking voltages in a radio, unless otherwise told to, like in any type of voltage chart or any instructions that's on the schematic, your negative lead will be connected to basically the DC ground. Now, I say DC ground or B minus mainly because you could be working on like an All-American 5 or something of that nature, a radio that don't have a transformer or anything, and it's got a floating chassis where the chassis is not actually ground. The ground is throughout the radio with wires, and that's also known as the B minus. But otherwise, other than a little situation like that, in any case, the negative lead of your voltmeter will always pretty much remain on ground, and then you use the positive lead to probe for your voltages, and that includes the grid voltages. And if they're going to show up, you got to realize sometimes, depending on the circuit and stuff, you may only get like 0 volts there, or maybe a negative 0.6 or 0.2 or something like that, because all voltages technically are referenced from the cathode. Now, if the tube, the cathode actually goes directly to ground, then you're going to get an accurate read on the grid voltage. Otherwise, you'll get something a little different than what's really going on the grid. As long as it's either 0 or negative, it's perfectly fine. So I just wanted to answer that real quick. Very seldom would you ever run into a situation where they'll want you to hook up somewhere differently as far as your meter. So that's basically how you check for the negative voltages. Now, the first comment I want to catch on is Art put on here, made a comment, and left a link up here, and that is an excellent link for anybody who's wanting to try to understand a little more about the circle and the triangle and everything on the math that we've been talking about. It's got some really good animations there and stuff. So check it out. I think it'll help you really understand if you're having little troubles with it and stuff. And thanks again, Art, for putting that on there for everybody. And since you're doing such a good job of that, I think I'll just go ahead and make you my TA, teaching assistant. So anyway, no, it's a great site, and you'll find some really good animations that really answer a lot of questions if you have them. So check it out. Let's see here. Okay. Delta Kilo 915, I think I'm pronouncing that right. You want to know a little bit about, I haven't done a video strictly on design of power supplies, um, but just to kind of, I will be doing one probably. Well, I definitely will be. I'm not sure exactly when. It'll be sometime in the future, sometime probably this summer. I did draw up something just to kind of give you a general idea. One thing I want to mention here, when just I don't know, maybe from your question or anything, but I'm gonna at least answer this question somewhat from the standpoint of building a power supply for, radio or an amplifier or whatever, as opposed to a benchtop type power supply. There's a little difference between the designs of them, slightly. But your basic design is going to be something of this nature. You're going to have, your transformer, your secondary, that'll be tapped to get a full wave if you want to full wave rectify it. You can do it without a center tap, but then you'll have to use 2 tubes. This is a better way of doing it, a little cheaper. And then you just got your rectifier tube, the plates hooked to the high voltage, and then you'll have you either have a directly heated cathode like I show here, or an indirectly. Doesn't matter, but the filament or heater will hook to 5 volt. In most tubes there are some 6 volt tubes. That will be feeding your B plus through a pi type filter, 2 filter caps. They'll connect to ground, and a choke. You can put a resistor in here instead of using a choke, but a choke will give you a much smoother output, less ripple, with smaller caps involved, and then that just goes straight to B plus. If you notice, there is no bleeder resistor in this circuit, mainly because it's not necessary. This will attach then attach on to a radio or an amp or something that is powering, test equipment, whatever. When you shut the power off, the tubes stay hot for upwards over 30 seconds to over a minute, depending on how long it's been on. They will still conduct, which will bleed these capacitors off pretty darn quickly. Usually within 4 seconds they're bled off. So you don't need one. Now if you was building a bench supply, that you can use as a universal power supply for powering up experiments, powering up a radio that is battery operated, whatever, then you would put a bleeder resistor in. But as far as choices of parts, the tube, really the 2 main things about the tube that you're looking for is its current carrying capabilities. You want a tube heavy enough to handle the current draw through the power supply, whatever it's going to be powering will be drawing. And the other one is the peak inverse voltage. That is the voltage when you're trying to flow the current backwards through it. When your waveform on your AC goes the other direction and you're trying to reverse flow through the tube, you want at least 2 times the standard voltage of what the power of the transformer can put out for that rating at minimum. So, and both things are shown up in tube manuals. And and as far as like picking out a transformer, basically what you're looking for is, what voltage do you need, what current you need to run your radio. Those are your basic options, or the things that you're looking for. Another thing is where you live. Do you have 240 at your mains, or do you have 120 at your mains? So that will determine your primary. Capacitors, that varies. If you're running a decent sized choke, somewhere around 4 to 10 Henry choke, you can get by with 10 microfarad for an input, and an output cap I'd probably run around a 33 microfarad, something of that nature. And these voltage here, depending on what this is, should be, if you run transformer power supply, you're probably looking at least somewhere around 450 volts. Really would be a good choice for the voltage on the caps. So anyway, I hope that does answer some of your questions a little bit. I will be doing a video series on power supplies, but it'll be later on, a little bit later this summer. Phil, it's nice that you do the catch up, but then you swamp me with comments, which I appreciate your comments. I love reading them. Basically, yeah, bringing back memories on the math and stuff and everything, yeah. And I do find that interesting about the humbucking coils over there. I over here, most radios, well, at least most radios that had had field coils, the dynamic speakers had humbucking coils in them, and most of the radios here. Basically, I think really where you found any cost cutting or least expensive radios would have been, what they did was, if they did have a transformer and stuff in them, would be they just cut down on bands, just be a single band radio, probably no tone control or anything of that nature, but they still had the humbucking coils in them. Anyway, thanks, Phil, for all your comments and your gracious words. I really appreciate them. Let's see here. What else? Okay. Oh yeah. Tom, Antique Radio and TV. To answer your question, yes, a 2 pi's 360 does mean that half a 2 pi would be half a 360, so 1 pi is 180 degrees. I kind of drew this out. You go the full circle and you get 2 pi or 360 degrees. A half a circle, you're going to get a single just pi radians, 180 degrees. Half that again, say 90 degrees, is pi over 2 or 1/2 pi. Half that again for 45 degrees, you get pi over 4 or 1/4 of a pi. And just any other variables if you want, but yeah, that's it. It's basically linear through around the circle. I will be making a video this week on the second part of the math, and I'm going to start on the schematics, and oh gosh, I got a bunch of things to do. I believe there was some talk or somewhere, I think I remember reading one of the comments. Yeah. I wanted to show a little bit more about the humbucking. I'm actually surprised you guys really like that information. To verify something for you, I want to correct you. With a humbucking coil, as far as direction of winding, which way they're actually the same direction as the field winding. What actually happens is anytime you induce voltage into a winding by a magnetic field, in other words a moving magnetic field fluctuating, will induce a voltage in. It is in counter. It's counter EMF. It's in reverse of the voltage that is producing the magnetic field. And what that means is say like right here, if the blue line represents the ripple that's on the field coil, when it starts, it's changing all the time. So as it changes, it's producing a magnetic field that's changing. So as it's going positive, the humbucking, the counter EMF that's producing it's going negative. And it'll be the same if the coils are wound properly. In other words, a right number of turns in a humbucking coil, they'll be of the same magnitude, so that they cancel each other out. So let's say if this is going 1 volt positive at peak, this will be 1 volt negative at peak, and if you take 1 volt, subtract 1 volt, you get 0 volts, and that's how it actually works. And it'll just flow right on through doing that. So I wanted to kind of clarify that a little bit, and I know this thing's moving around like a ton of weeds. So that, and yeah, Tom, I hope you're not smoking any of that Dutch cleanser. But I just wanted to, for anybody that needed it clarified, or I hope that helps anyway. Let's see. A lot of you just thanking me for doing these videos. And how much you appreciate me doing these. I enjoy doing them. I consider it a blessing to be able to do these anyway, and that you guys are enjoying them and getting something from them. Yeah, I'm glad I was able to show you that, John. I didn't realize you'd never seen one before. They're on the humbucking coils. And thanks for commenting. Yes, Al. So what will your first musical selection be? Well, and that goes back to the Thaman musical instrument. I'll tell you what, I want to keep viewers. I may be able to build the thing, that's not a problem, but playing it, that's a total different thing. I'll show that it works. It makes noise, and it can make god-awful noise. But to attempt any type of playing of it would be, well, probably it'd be almost like suicide. It'd just be terrible. So other than just showing the thing does squeal a little bit and make some noise and explain the operation of it and why it's doing what it's doing, that's about as far as the playing of it's going to go. Let's see. You guys really did enjoy the math, so I'm glad of that. So anyway, yeah, Jake, made a comment about trying to imagine the theremin's circuitry. It's actually a pretty simple circuit. It's not complicated. In fact, I'm actually going to use someone else's schematic. It came out of came from Popular Electronics in 1955, I believe, issue. Yeah, I think it's like 5 tubes, and that's including the rectifier tube. They're not real complicated. Basically, the tones section of it is nothing more than just a local oscillator, and there's actually 2 oscillators. A local oscillator that the stationary frequency doesn't change, and then the antenna is hooked to another oscillator, and your hand movement, by changing the capacitance, is changing its frequency, and the 2 are mixed together and sent through an audio amp and out. The other circuit is pretty simple, just a driver to and a little bit of circuitry there to adjust volume by use of changing capacitance. So it we'll go over the circuit when I get close to getting ready to build it and stuff. So I think I pretty much caught most of these up, I hope, and I did want to kind of show you, kind of started on a little something else in the interim time period here. I'm still working on a couple others, you know, the 62407 and then another radio. The one started is a German radio. It's a Kaiser, and actual model number. This schematic is pretty well the same schematic. They use this same chassis pretty much in several models. The model on this, the actual what it is a W1648, I believe. But this schematic works just fine, which is for W645, 48, and 49. There's only a couple little minor differences. They're real minor. I'm just getting started on it. Had to strip her down. She's pretty rusty. Here's some pictures of it. As you can see, it was not in the best condition, which is kind of surprising because the cabinet is not actually too bad a shape. Nothing like what the radio showed on it. So, but you know, the chassis was pretty darn rusty and everything. So, both the bottom and top of it. Get to some of the bottom pictures here in a minute, and yeah, you can see some really nasty little rust in here. So I decided to just strip her down and everything. Now surprisingly, so far in all the components, every resistor I've checked, I've only got probably about 3 or 4 yet to check, have been right smack on the money. The capacitors, on the other hand, these black molded things, this one's was just literally exploded up, and most of the rest of them are badly cracked, and they're all leaky. So a couple things I wanted to point out on this thing. That was kind of funny. It has a well, the fuse goes here, and it had ability to switch it from 110 to 125 and 220, and it shows that in the schematic right here, where you can switch for different voltages. Well, this thing was tucked up. You can see it right here. It's kind of tucked up underway, and it was dirty and everything. It wasn't until I started dismantling it that I noticed something. Now you'll notice here on the transformer there's these 2 tubes. It's got wires going in them. Well, what they are is they had folded these wires up, and it's kind of hard to see, but they had left them long and then folded them all up and then stuck this kind of like heat shrink, or, well, here, this one comes off really good. That's how they had them. And those happen to be the other parts of the primary winding. They put the switch in, but the switch will only work for 110 because it has no other contacts here. They went through the trouble of actually making this thing. I mean, the main switch arm is screwed onto place, and put all this in, left the wires long, bought the transformer for it, and then just folded them back like this, but didn't bother to rivet in the other 2 contacts. So I thought that was rather interesting that they go through that much trouble then not really finish it. So anyway, this thing's starting to get long, but I did want to answer some of those and kind of show you kind of a future project. When we, I'll be, tomorrow probably will be when we start on, I want to do a start on the schematic video, and I'm going to probably show 2 or 3 schematics. One will be this one because of some things that's on it, and the fact that, you know, you may buy a radio from overseas. You know, there were a lot of them imported here. This was actually imported. In fact, they talk about import and stuff. So I just wanted to, you know, show you some differences between like this schematic and what you might be used to seeing, and stuff like that. In our first video, we'll probably talk about, I know some of you probably would like to dig your teeth right into reading the schematic, but one of the most important things is in reading a schematic is understanding the symbols, and you know, that's really good for pretty much anything and everything. And I want to point out some stuff. This one's actually using symbols for resistors that are being used, if I can see my pointer here. These are resistors here, little just rectangular boxes. That is what's used in modern day schematics today, to when they draw up schematics, or at least a lot of them are drawn that way. Now this is from 1956, I believe, 56, 57, somewhere in there. So anyway, trying to think if I had anything else to say. Not particularly that I can think of right now, but I'll start on that schematic video tomorrow. It probably will start out kind of long, mainly because I want to get through the symbols and some of that stuff and some information on that, and kind of at least get a general start. And but anyway, I'll try to use a schematic of a more simpler built radio, something that you guys can look up, you know, like off Nostalgia Air. That's kind of, you know, that you can read it, you know, it's a good scan. And then another one that I know you can get access to, and just to kind of give you, you know, some different perspectives, and then just kind of show out some of the differences and stuff and drawings in this and everything. So I guess until tomorrow and stuff, again, I truly appreciate all your comments, and I'm sorry that I just didn't get back to them very quickly. The weather had been starting to warm up, and the wife had a lot of honey-do list stuff to do outside, like getting the garden prepared and everything, and a lot of her planters and a bunch of other stuff, which I didn't mind too much because I've been getting pretty good cabin fever going, so I was kind of glad to actually get outside and actually enjoy the weather, even if it meant doing work. But anyway, so until next time, thanks for watching, and thank you for your comments and your support. You guys are really quite gracious in your support of me, so I appreciate it. See you on the next video.